Today we're going to solve a problem concerning helical springs and their shearing stress. This particular problem can be found on Strength of Materials book, 4th edition, by Engr, Pytel, and Ferdinand. So this is problem 350, and it reads as follows. As shown in the figure below, a homogeneous 50 kg rigid block is suspended by the 3 springs whose lower ends were originally at the same level. Each steel spring has 24 turns of 10 mm diameter wire on a mean diameter of 100 mm, and it has a modulus of rigidity of 83 gigapascals. The bronze spring has 48 turns of 20 mm diameter wire on a mean diameter of 150 mm and a modulus of rigidity of 42 gigapascals. Compute shearing stress of each spring. So as you can see, the figure is as follows. So we have 3 springs, 2 of them are steel and 1 is bronze. So the 2 steel springs are separated by 1 meter, and the phosphor bronze is 2 meters away from the second steel spring. So first of all, I'd like to denote the force from the first steel spring as P1, the force from the second steel spring as P2, and the force from the bronze spring as P3. So to start with, let's list down the given variables. So in the problem, we are given the parameters of the steel spring. So it has 24 turns. It also has a wire diameter of 10 millimeters. It has a mean diameter of 100 millimeters. However, I'm going to convert this to mean radius because in the equations on the book, mean radius is often used instead of mean diameter. So mean radius is 100 millimeters divided by 2, which is 50 millimeters. And its modulus of rigidity is equal to 83 gigapascals. So this is the parameter for both steel springs. So both steel springs are identical. Next, we have the bronze spring. For the bronze spring, it has 48 turns. Its wire diameter is equal to 20 millimeters. Its mean radius is equal to 150 millimeters divided by 2, which is 75 millimeters. And it has a modulus of rigidity of 42 gigapascals. Sorry. Also, for this problem, we're going to use the acceleration due to gravity. We're going to set it at 9.81 meters per second squared. Now, since we're being asked to calculate the shearing stress, so it's worth noting that the equation for shearing stress is equal to 16 times the force times mean radius divided by pi times diameter of the wire cubed times 1 plus diameter of the wire divided by 4 times the mean radius. So as we can see, we already have all of these variables except for the force P, which we will have to solve individually. However, as you may have already noticed, we have 3 variables for the force P. So we have P1, P2, and P3, and we can only generate 2 equations from the equilibrium equations. So we can only create 2. So I'm going to show you that right now. So first, we're going to create the free body diagram of the block. This is the 50 kilogram block. First, we have the force due to its weight, which is 50 times the acceleration due to gravity of 9.81. So that is 490.5 newtons. Then we have P1, P2, and P3. From the figure, we know that the distance between P1 and P2 is 1 meter. And the distance between P2 and P3 is 2 meters. Now, since this is a homogeneous block, we know that we can denote its entire weight as one force stemming from its centroid, which is for a rectangular block, it's in the middle of the block. Since this is 3 meters in length, then we know that this force is found 1.5 meters away from the edges. So now we're ready to obtain our first equations. So first we have summation of forces along y, upwards positive. Then we have P1 plus P2 plus P3 minus 490.5 newtons is equal to 0. So this is our equation 1. Next, we have the summation of moment calculated from this point, which is the point from the first steel spring. So summation of moment at 1, I'm just going to denote this as moment at point 1, is equal to 0 clockwise positive, since this is what I'm used to. If you're used to counterclockwise, then you can solve it that way. So we have P2. This is counterclockwise, so negative P2 times 1 plus clockwise for 90.5 Newton times 1.5 meters. Let's just write this after P3. So P3 is 3 meters, also counterclockwise. So minus P3 times 3 plus 490.5 times 1.5 is equal to 0. We can clean this up a bit. I'm going to multiply all of this by negative 1. So we have P2 plus 3P3 minus 735.75 is equal to 0. And this is our equation 2. So as you may have noticed, again, we have 3 variables for the force, P1, P2, and P3. However, we only have 2 equations. So we need to create another equation, or we need to find another equation which is an accurate representation of the relationship between the forces. So this is essentially a statically indeterminate problem which describes this exact situation. So in order to move to the next part, let's start out by creating that equation. So I'm going to redraw the block again. So assume that this is the block. And these are the springs. So we know that springs elongate. In fact, we have an equation for the spring elongation. If these 3 springs elongate, we can assume that the final or the end position of the block will become like this. Sorry for the drawing. Where this is the elongation of the first steel spring. I'll denote this as delta 1. This is the elongation of the second steel spring, delta 2. And this is the elongation of the third spring, or the bronze spring, which is delta 3. So you may have noticed that I've assumed that the bronze spring elongates longer than the steel springs. I've made that assumption because first I'll write down the equation for elongation of helical springs. Elongation of helical springs is given by delta is equal to 64 times the force times mean radius cube times number of turns divided by the modulus of rigidity times the diameter of the wire to the 4th power. So this modulus of rigidity is an accurate representation of how rigid a material is and how much it resists being stretched out. So since our steel springs have higher modulus of rigidity, so you can expect that this number goes down because it's in the denominator side. Another thing is the bronze spring also has, aside from it having lower modulus of rigidity, it also has higher number of turns, and it also has a higher mean radius. So we can expect that this number will be bigger for the bronze spring. However, that's really not set in stone because your force can change. So mostly it looks like this, but sometimes with differing forces, it can be different, and our calculations may or may not support this. And if it does not support this, then you're free to change your assumption, your illustration. Anyway, let's move on. So you can note, we can make a horizontal line here, whereas, or such that this part, this small part, I may have drawn this a little smaller, this part we can denote as delta 2 minus delta 1, and this part can denote as delta 3 minus delta 1. Now, you may have noticed that this, we have we formed two triangles, this triangle and this triangle. And these two triangles are similar. It has the same angles. So it should follow the rules of similar triangles such that these two sides, the ratio of these two sides would be equal. So this length here, we already know for certain that it's 1 meter. And this one is 2 meters. So we should know that the ratio of this side, which is this, divided by 1 would be equal to the ratio of this side divided by the total, which is 3 meters. So that's our, well, that's the beginning of our third equation, since we have to convert these to force first. So let's clean it up a bit better. So we multiply 3 on both sides, or we cross multiply. So we have 3 times delta 2 minus 3 delta 1 is equal to delta 3 minus delta 1. Then we move this to this side. 3 delta 2 minus 2 delta 1 is equal to delta 3. Now, we put this entire equation and we substitute each one with this. So how that looks like is, I'll just write it here, this side. It's going to look like this. 3 times So 64 times, this is 2, so force number 2, or force from steel 2, times its mean radius, which is 50 cube, times number of turns, 24, divided by its modulus of rigidity, which is 83, and its wired diameter of the wire, which is 10. Minus 2 times 64 P1 times mean radius 50 cube times 24 divided by modulus of rigidity times diameter of the wire is equal to 64 times P3 times 75 cube times 48 divided by 42 times 10, oh wait, 20 to the 4th. So one thing you should notice is that I didn't convert any units at this because these are basically just ratios. So for example, I convert this to, or I use the actual conversion for this gigapascal, since this is in gigapascals. So let's say this is 42 times 10 to the 9. This is also, this becomes 83 times 10 to the 9. And this becomes 83 times 10 to the 9. So as you may have noticed, these gets cancelled out. I'll use a different color. So these will essentially just get cancelled out. So that's why units don't matter in this portion. Furthermore, we can cancel out other values to make the calculation easier later on. So these 64 are present in all three. And lastly, this 24, we can cancel out. And this, we have 2 left. So from that, we can use our cycle to solve the equation, or to create the equation. So for this, we have 3 times 50 cubed divided by 82 divided by 10 to the 4th power. So that's the screen. No wait, not 82. That's 83. There. So that's 75 over 166 P2 minus, for this is exactly the same, except this becomes 2. So we have 25 over 83, or 50 over 166 P1. Then lastly, we have 2 times 75 cubed divided by 42 divided by 20 to the 4th. So that's 225 over 1792 P3. So I'm not converting this to decimal because first of all, fractions, well, the main reason is fractions hold more accuracy or hold more precision compared to decimals. You are less likely to get rounding off errors using fractions. So I'll convert this later on at like the final parts of solving this. Anyway, so this is our equation 3. Equation 3. Now we have 3 equations and 3 unknowns. So this should tell you that we can solve this using just basic systems of linear equation techniques. So let's list. Let's list them down again. So P1 plus P2 plus P3 minus 490.5 is equal to 0. Then the second one is negative P2. Actually, no, still positive. P2 plus 3P3 minus 735.75 is equal to 0. Then, lastly, we have this, which is negative 50 over 166 P1 plus 75 over 166 P2 and negative 225 over 1792 P3 is equal to 0. So from this you can already solve this if you know how to use the modern functions in the scientific calculator. Like you can just plug this in and it will give you P1, P2, and P3. However, I do like to solve things manually, so I'm going to solve this manually. And the first thing you should do is, since we have this second equation is missing P1, we need to cancel out P1 from the we need to use the first and third equation to cancel out P1, so we're left with P2 and P3, which we can use together with the second equation to get one of the variables, or the value of one of the variables. So to do that, I'm going to multiply this, use a different color. So I'm going to multiply this by 166 over 50, which is the reciprocal of this value. That way we are left with negative P1 plus 3 halves of P2 minus 747 over 1792 P3 is 0. Then we'll just copy the first equation here. We have P1 plus P2 plus P3. I guess it's time to move this constant to the other side, which is equal to 490.5. We add all of these. So we get, this one cancels out. This is 5 halves P2. This one is plus 1045 over 1792 P3 is equal to 490.5 newtons. So now we have two equations with two unknowns. So next I'm going to do is I'm going to divide this or multiply this by the reciprocal, negative reciprocal of this to remove P2. So again, I'm going to use a different color so that each step will clearly be divided. So we're going to multiply this by the negative reciprocal 2/5. So we end up with negative P2 minus 209 over 896 P3 is equal to negative 196.2. So we're going to copy the second equation again. That's P2 plus 3P3. We're going to move this to the other side, equal to 735.75. Then we're going to add this up. This gets cancelled. So we have 3 minus fraction 209 over 896. That's 2479 over 896 P3 is equal to 735.75 minus 196.2. That is 10,791 over 20. Then we divide this value by this value. So divide by 2479, 896. We get 195.01. So P3 is equal to 195.01. Next, we're going to substitute this P3 into the second equation to get P2. So let me just use another color. So we have P2 plus 3 times 195.01 is equal to 735.75. Thus, we get P2 is equal to, let's store this first. Wait, no. Minus 3 times C, that's 150.71 newtons. Lastly, we're going to substitute both of these values to the first equation. So we get P1 plus 150.71 plus 195.01 is equal to 490.5. So for this equation, we have 490.5 minus, I store this as B and I store this other one as C. Oops. 144.78. So P1 is equal to 144.78 newtons. So we have all three forces. Now we can, we already have all the variables that we need to calculate shearing stress. So let's go back to shearing stress now. So again, the equation for shearing stress is (16) times the force times mean radius over pi times diameter of the wire cube times 1 plus diameter of the wire divided by 4 times mean radius. So now for the shearing stress of the first steel spring, I'll use red. So first steel spring is equal to 16 times force of the first is 144.78 newtons. And for this, the units actually matter now, so you have to include the conversion to standard. So for example, for the mean radius, we used millimeters. So now I'm going to make it into meters. So this becomes 50 times 10 to the negative 3 over pi times diameter of the wire, which is 10. So 10 times 10 to the negative 3, since this is in millimeters also, cubed, multiplied by 1 plus diameter of the wire, 10 times 10 to the negative 3, divided by 4 times mean radius, which is 50 times 10 to the negative 3. So we can cancel this out. Also, we can cancel this out for all the future shearing stress. So it will always look like this. Anyway, we can use our cycle now to solve this. So we have 16 times, this is 144.78 times 50, 50 times 10 to the negative 3 divided by, actually let me make it look better in the cycle. 16 times 144.78 times 50 to negative 3 divided by pi times 10 times 10 to the negative 3 to the 3 cubed. Then multiplied by 1 plus fraction of 10 divided by 4 times 50. And we get 38,711,320. So that's 38,711,320.47 pascals, or 38.71 megapascals. So that's the first. So steel spring 1. Next, we'll do the same thing for the second steel spring. That's 16 times the force of the second steel spring, which is 150.71 newtons, times 50 to the negative 3 divided by pi times 10 times 10 to the negative 3 to the third, multiplied by 1 plus 10 times 10 to the negative 3 divided by 4 times 50 times 10 to the negative 3. Cancel out. So we get 16 times 150.71 negative 3 times pi. I think that's right. 4 times 50. Yep. So we get 40.9 9.30 megapascals, and lastly, we have for the bronze spring 16 times 195.01 times mean radius of 75 divided by pi times 20 times 10 to the negative 3 cube multiplied by 1 plus 20 times 10 to the negative 3 over 4 times 75 times 10 to the negative 3. So this gets cancelled, and we have D3 is equal to 60. 16 times 195.01 times 75 times 10 to the negative 3 divided by pi and divided by 20 times 10 to the negative 3 cubed multiplied by 1 plus 20 over 4 times 75. And we get 9.93 megapascals. Bronze spring. And that's it. We solved the problem. So if you have followed this or if you have followed me solving this far, then congratulations. You can now solve shearing stress for helical springs. Also statically indeterminate problems of this nature. So thank you for watching, and I hope you've learned a lot from me today. And see you next time. Bye.